Well, I guess it's time, 9 o'clock here in Baton Rouge. Our next speaker is Brian Wynne. And the title is The Freudenthal Spectral Theorem and Sufficiently Many Projections in Archimedean Vector Lattices.
Thanks.
Yeah, a little bit.
Okay, thanks. So I want to thank Chip and Jim for organizing this meeting and for giving me the chance to speak here today. The work I'll be telling you about is joint with Tony Hager. So this will be a talk about vector lattices, also known as Reese spaces. Just a real vector space with a lattice ordering where the ordering is translation invariant, and if you multiply a non-negative element by a non-negative real, you get a negative element back. All the vector lattices in this talk will be archimedean. So that's true from now on. So I'll be trying to, like we did, so I'm reporting on work in a paper that Hager and I wrote. And there in the paper, we tried to some extent to follow the notation in this book by Luxemburg and Zahn called Reese Spaces, Volume 1. And I think in some of the vector space literature, they use this D operation instead of perp, but D and perp mean basically the same thing here. So a weak unit is something whose double perp is the whole vector lattice. And just to remind you, I guess in the Reese space literature, they sometimes say disjoint complement for this set of all. If you're given a set from a subset of the vector lattice A, then the set of all things that are disjoint from everything in that set, that's this disjoint complement, and that means disjoint here means that the mean of their absolute values is 0. So we decided we had a bunch of notational difficulties in this paper, but okay, so we decided to use square brackets around an element. That means the ideal generated by that element. So that consists of, turns out that consists of all the elements whose absolute value is less than or equal to some integer multiple of the given element. An ideal in a Reese space is, in general, is an order convex of linear subspace. Okay, so strong unit is something whose the ideal it generates is the whole vector lattice. And another slight departure from the talks yesterday, I think. Here today, W will represent the category of Archimedean vector lattices with distinguished weak unit and unit preserving vector lattice homomorphisms. So we just didn't, since we're talking exclusively about vector lattices, we felt like it'd just be simpler to not call it W sub B or something like that. So W here will be just vector lattices, these Archimedean vector lattices. Okay, so the prototypical example is C of X. In this talk, X will always be Tikhonov, and in that case, if 1 here represents the constant function with value 1, that's a weak unit. In general, if X is compact, it's a strong unit. So our main tool in this work, and also the source of the question that we were trying to address, is this what we call the Yoshida representation theorem. This developed from a theorem of Yoshida, maybe the proof that Yoshida gave of a certain theorem. Anyway, so it involves this d of x. So you have a space x And then d of x is all the continuous extended real value functions such that the preimage of the reals is dense in the space x. So this d of x object is always a lattice, but but plus may only be partially defined. But if your space enjoys special properties, and so for example, if x is extremely disconnected, then this d of x is in fact a vector lattice. So the representation theorem says, okay, if you start with a W object, so that's a vector lattice, Archimedean vector lattice, and with distinguished weak unit, U. Then if you look at what are sometimes called the values of U, so these are ideals that are maximal with respect to not containing U. So if you give that collection of so that's a special collection of primes. If you give them the Hall kernel topology, then what you get is a compact Hausdorff space, and there's a vector lattice embedding of your original W object into these continuous extended real value functions that sends the weak unit in your original vector lattice to the constant function with value 1. And the functions in the image, they separate the points of the Yoshida space. In fact, they 0, 1 separate the closed sets. And this Yoshida space is unique for that data. And I'll sometimes just indicate that the Yoshida, basically the Yoshida representation will be in play almost every time we're working with a W object in this talk. But sometimes to remind you that that's going on, I'll write A is less than or equal to this D of the Yoshida space. And sometimes, so of course, the representation you get actually is sensitive to which weak unit you choose. So if you change the weak unit, you can get a very different space. So properly, you should probably say Yoshida space of A with particular, but a lot of times when the weak unit is sort of clear from context, I'll just write Y of A for the Yoshida space of A. All right, so this project got started when I was working on another project, unrelated, and I was trying to determine whether certain L groups had Yoshida spaces that were 0-dimensional, and so I thought there must be some very well-known condition for this. So I wrote to Tony and asked him, what's the condition when Yoshida space is 0-dimensional? Oh, 0-dimensional here just means there is a base of clopen sets. So if you just start, what conditions on A will guarantee that the Yoshida space is 0-dimensional? And so he got interested in this. I guess he had already answered this question once before in a paper with Kimber and McGovern in 2013 or something. It was sort of a corollary of some other work they were doing. They came up with a characterization, but Hager had sort of in rethinking about it this time, he had a sort of new insight. So that was what we pursued. And there was a related question here: when is the Yoshida space high ZD for short? Meaning pi 0-dimensional, which is short for there is a pi base of clopen sets. So this means that if you take any open set in the Yoshida space, a non-empty open set in the Yoshida space, then there must be some non-empty clopen subset. Okay, so I want to tell you about the answer that we found to this question. So this is sort of part of a relatively long tradition of trying to understand the relationship between the W objects and their Yoshida spaces. So that's how I see it fitting into early work. Okay, so the answer that we came up with involves approximating functions by simple functions, if you will, which I'll try to describe now. So if you take a non-negative element, we want to start by looking at its components, and then take the linear subspace generated by those components. We're calling that lin comp of E, for lack of a better, but we won't be using that too much. I mean, I'll quickly move away from this notation. But okay, so in the special case of a W object, remember in the representation, we think of this distinguished weak unit as a constant function with value 1. So then these components are just the characteristic functions of the clopen subsets of the Yoshida space. So, and in particular, then the linear subspace they generate can be expressed in this alternative way, which I'll use more frequently from now on. It's the F of the Yoshida space is the collection of all continuous functions on real value continuous functions on the Yoshida space that have finite range. So what we're going to be doing is approximating other functions in A by these functions. Okay, so here is one of the conditions that we looked at. So the notation UD square brackets E is saying that the linear subspace generated by the components of E is uniformly dense in that ideal. So that just means that, or I should say E uniformly dense, because E at the moment is just an arbitrary non-negative element. So that just means there's a sequence in the linear subspace generated by the components of E that if you look at any positive real multiple of this element E, then the absolute value of A sub n minus A is less than or equal to that from some point on. So this is sort of like the generalization of the more familiar uniform density, one uniform density. And then another condition, related but different condition, is this ODE double perp or EDD. OD here stands for order dense. So this time we're saying that the linear subspace generated by the components of E is order dense in this principal polar. Oh, I should say, so we're in Archimedean vector lattices. So if you're more familiar with L group terminology, polar and band mean the same thing. I'm going to use the word band in a few minutes again. So anyway, here the principal polar EDD has these guys order dense in it. That's what this ODE condition stands for. And that order dense here, you can say it a couple different ways. One way is in the sort of approximation way of phrasing it is that if you take a positive element in EDD, then it is the join of some elements in the linear space, subspace. Another way of saying it is just if you take a positive element EDD, then there must be something in lin comp E that is below it. So these are the two different forms of approximation that we looked at. Actually, we looked at a couple others too. There's more in the paper than I can say here in the talk. So check it out if you're interested. Okay, so this is the theorem that we came up with. So for a W object, the Yoshida space is zero dimensional if and only if that those finite valued functions with finite range are uniformly dense uniformly U dense in the ideal generated by U. And sort of parallel to that is that the Yoshida space is pi zero dimensional. That just means pi base of clopen sets, if and only if this ODU condition holds. when I originally wrote these slides, I guess I was feeling kind of ambitious, so I wrote down some sketches of the proofs, but I'm a little worried that I won't have time. But let me at least mention one thing that we thought was interesting here is that the left to right direction in the first property is basically just the Stone-Weierstrass theorem, because if your Yoshida space is zero dimensional, then the functions with finite range, they separate the points. And so the Stone-Weierstrass theorem says that you get this uniform density. Okay, maybe if there's time, I'll come back to some of these proofs later. Okay, so I want to give the statement here of our version of the FST, which is the abbreviation. So, like I was saying earlier, band and polar mean the same thing. So if you know what polar is, then you already know what band is in this context. So band, when I say band, I just mean an order convex linear subspace. So closed under arbitrary suprema, just meaning that if you take a collection of elements in B, if they have a supremum in A, then that suprema must live in B. And then one of these bands is called a projection band if A is a direct sum of B and its disjoint complement. And then the vector lattice is said to have the principal projection property, PPP for short, in every principal band. So that's one of these, take an element and look at its double verb, is a projection band. And in fact, it's shown in Luxemburg and Zanen that this implies that the vector lattice is archimedean. But for those of you who are more familiar with L groups, the analogous property in L groups is called projectable, but they're not exactly the same because in L groups, projectable does not imply archimedean. So, okay, so this is our version of the FST. It's kind of like if you look in Luxemburg and Zanen, they give the FST in two parts, and corresponding to the two conclusions here. And this is sort of the core of those theorems as we see it. I mean, they involve a lot more bells and whistles, because I think they're setting up to do integration theory. But okay, so this is what it says. If you have a vector lattice with PPP, then for every non-negative element, you can do both of these kinds of approximations, UDE and, okay, SODE is the strictly order dense. So remember, order dense just meant that you take every element in EDD is the supreme of some elements in the approximate functions. Well, strictly just means that you can have that sequence of functions be increasing. And I didn't introduce the strictly part earlier because that's actually turns out is equivalent to UDE always. So it won't be coming up again. I'll be just to keep it short. So this is a theorem, and this is our sort of Yoshida-based proof, which is manageably short, at least in outline here. So the idea is if the vector lattice you start with has PPP, then if you take a non-negative element, so remember A here might not be a W object, but I mean it's Archimedean for sure because it has PPP. But if you pick an element, a non-negative element, and look at the ideal it generates, then that element will be a weak unit in that, in fact, a strong unit in that ideal. So that is a W object, and it turns out that W object inherits PPP from A. And then work of Hager and Martinez, for example, showed that if you have PPP, then the closure of each cozero set is open. So that leads to the Yoshida space of this sort of local Yoshida space. This will be coming up. Y sub E is the Yoshida space of this associated with the ideal, principal ideal generated by some particular element E. So that Yoshida space will be ZD. And therefore, by the previous theorem on the previous slide, it'll have both of these approximation properties. So that was an outline of our proof. And if you're familiar with Hager and Martinez's result here, they characterized PPP, and half of the characterization is that closure of co-zero sets must be open, but there's another piece. And so that suggests that you don't need the full strength of PPP to get these conclusions of the theorem. And it turns out that's the case. And in fact, a couple of people had looked at this in the past. But this was the question that we then tried to address. So when do the conclusions of FST hold? And we can have rephrased that in several ways now. So the sort of order algebraic way is for every E, we have this approximation result condition. Or you could say, another way of saying that is that for every E, this local Yoshida space is zero dimensional. And then the other conclusion is that for every E, we have this other kind of approximation condition. Or you could say for every E, the local Yoshida space has a pi base of clopen sets. So these two conditions are equivalent in the presence of PPP, but when PPP is not in effect, then they can be different. So then the question is, when do we have these other conditions? What can we say? How do you, how can you tell that all these local, if you start with some Archimedean vector lattice, how can you tell when is it going to happen that all of these local Yoshida spaces will be zero dimensional, for example? So this is the method that we tried to employ. So let's say we start with a W object, and then think of it in terms of the Yoshida representation. So if you take a non-negative element, now not just any non-negative element here, so if you take one that is bounded, so meaning that it lives in the ideal generated by the distinguished weak unit. Remember, in the representation, that weak unit U gets sent to the constant function with value 1. So the representation of this little E will be bounded in the representation, an actual bounded function. Okay, so the first step is we represent this sort of local W object inside the bounded continuous functions on the co-zero set of that element. So this gets a little. There's several representations happening here. So co-zero of E is relative to the Yoshida representation of the original W object, AU. Now we're taking this sub-object and representing it in a slightly different way. So you take a function in the ideal generated by E and you basically divide it by E, and that'll get you, because F was in the ideal generated by E, it's below some, its absolute value is below some integer multiple of E. So when you divide by E, you get something that's bounded, still continuous. And you can show that the image of this local W object separates the points of co-zero E. So then its Yoshida space must be the minimum compactification of co-zero E over which all functions in the image extend. There are two natural candidates for that space. One thing you could do is you could take the closure of the co-zero set of E, that'll be compact Hausdorff, and all the functions will extend. So maybe that's this Y sub E. Or there's another option would be beta of the Stonecek compactification of the co-zero set. So these are two options. And if the original W object has a zero-dimensional Yoshida space, then both of those candidates are also zero-dimensional. So it's starting to get at this condition of where all the Y sub E's are zero-dimensional. So one might hope maybe that these y sub e's are always one of those two things, but they don't have to be. Here's an example. So let alpha n be the 1-point compactification of the natural numbers, and k here is any compactification of the natural numbers that is not zero-dimensional. There are such things. And little e here is going to be the function on the 1-point compactification that takes the value 1/n at n and the value 0 at alpha. And here is the W object, A. So you start with all of the functions, continuous functions on alpha n that have finite range. And what you add to that, I'm calling here, just to be short, psi sub e of c of k. So psi sub e is an embedding of c of k into c of alpha n. And that goes in the following way. So if this function e that lives on alpha n, you can think of that as a function on k by just defining it to be 0 at all points of k that aren't in n. So this extension of e to k, you can multiply, if you multiply the functions in c of k by e, it kills off all the non-zero values that those functions take on k, and because the natural numbers is dense in both of those spaces, you get an embedding. So of c of k back into the continuous functions on alpha n. So this is the object, and then little e is in there, and the Yoshida space turns out is alpha n, which is zero-dimensional, but the local Yoshida space of this element e is the k compactification that we specifically chose not to be ZD. So whenever the Yoshida space of your W object is ZD, then both of these candidates that I mentioned up here, they must be ZD. So this shows that this y sub e doesn't have to be either of those guys. It's not the closure of the co-zero set. It's not the Stone-Check compactification. Okay. So here are some of the things we found. These are some places where the conclusions, or at least some of the conclusions of the FST hold. So a C of x has this condition where all of its local Yoshida spaces are zero-dimensional if and only if x is strongly zero-dimensional. Some version of that result was proved by a previous author, but without using any representation theorem, and so their characterization was expressed entirely in terms of order algebraic structure of the vector lattice. And then I think one that was completely new was the next theorem, saying that if you have a W object whose Yoshida space is zero-dimensional, and if it has this property that the co-zero set of a non-negative element is C star embedded in the Yoshida space for every such E, then A satisfies this conclusion of the FST. In other words, all the Y sub E's are zero-dimensional. So some instances where the hypotheses of this theorem are satisfied are when, if you take a compact space K that's zero-dimensional and look at all the functions that have finite value, that have finite range, that obeys the hypotheses of that theorem. And then if you take any W star object, so W star means that the weak unit is in fact a strong unit. So if you assume that the unit is strong, then the Yoshida space is zero-dimensional F space, then you also get these same conclusions. So this condition, actually, we haven't seen studied. We're not sure if anybody studied this condition. Thought it was sort of interesting. This co-zero set of E is C star embedded in Yoshida space for every E in the W object. This is some kind of C star embedded just means that every bounded continuous function extends to a continuous function on the Yoshida space. Yep.
Think about the condition just in general without the ZD bugs?
I don't think we did. No, well, we wondered because it's sort of a natural variation on the F space condition. because F space condition is, I think, C star, for you can say X is an F space if every co-zero set is C star embedded. And so this is some kind of variation for W objects, but we don't know if anybody's looked at.
Any hyper-archimedean in bound array
I guess.
would have that journey. All co-zeros.
Oh, yeah.
So your YA can be as far away from being F space.
Oh, I see, yeah.
Interesting.
Okay, so this leads to the other, so we were looking at these two, so running in parallel. What Yoshida space is zero dimensional and Yoshida space has a base of clopen sets, pi ZD. And we found the connection between the pi ZD and this condition called sufficiently, we think this may have originated in Luxemburg and Sannon's book. A vector lattice has sufficiently many projections if every non-zero band contains a non-zero projection band. And they show that the principal projection property implies sufficiently many projections, and they both imply archimedean. So what we found is the connection here is if A has SMP, then its Yoshida space is pi zero dimensional. And originally, when we were first working on this, we thought it was if and only if. And we thought that a previous paper on this topic, which had claimed that there was an example, counterexample going the other way, was wrong. But then we found out that we were wrong. But anyway, so interestingly too here, unlike the zero dimensional case, if the Yoshida space is pi zero dimensional, that's equivalent to saying that all the local ones are pi zero dimensional. So that wasn't the case for just if you drop a pi, that statement, the analogous statement is not true. Now, if you assume that the weak unit is a strong unit in part 3 here, then the two are equivalent. SMP is the same as saying that the Yoshida space is zero dimensional. So one of the previous authors, so in a paper from 1992, said that there was an example showing that the converse of 1 is false, given in a paper of Wechsler from 1976. Unfortunately, that paper is in Russian, and neither Hager nor I read Russian. So we ignored that for a while and tried to think of one ourselves. So we came up with some, what we think are simpler examples. We eventually did get an idea of what the example was in Wechsler's paper, and if I have time, I'll say what it is. So we came up with our own examples, so that's what I want to show you now. Before that, so what exactly is going on here? What's the missing ingredient? So there was this, if A has this sufficient many projections, then its Yoshida space is pi zero dimensional, but the converse is false. So what exactly is the connection, or what's going on here? And it's the following. So remember when I was talking about the proof of the FST, I said that there in the FST, you assume the principal projection property, and that Hager and Martinez had shown that that was equivalent to co-zero closure of co-zero sets being open and some other condition. Well, this is where the other condition comes in. So we call lambda A all those clopen subsets of the Yoshida space that have this property, that whenever you take any element of A and you look at its product with the characteristic function of that clopen set, in other words, if you just chop it off and just look at it above that clopen set, then what you get is also an element of A. And that's not true necessarily of all clopen sets. Not all clopen sets necessarily have this property. And when they do, we say that they have local type, and it's a certain Boolean subalgebra of the full Boolean algebra of clopen subsets. That's connected. The reason for the terminology is it's connected with this idea of local functions on this W object. So remember, the W object is being represented inside this D of the Yoshida space. So it's all the continuous functions, continuous extended real valued functions on the Yoshida space that have pre-image of the reals dense. So if you we call log A the collection of functions in D of Y of the Yoshida space that are locally in A, meaning that if you take, so a function is locally in A if you can find some collection of open subsets of the Yoshida space and some collection of elements of A such that the given function on one of those open sets is equal to the corresponding function in A. So the function itself might not be in A, but sort of restricted to this collection of open sets, it is in A. And if all the functions, so every function in A is in log A, but they might not be the same. And if they are the same, then we call the W object local. And if the Yoshida space is zero dimensional, then A has to be the same as, or no, A is the same as log A if and only if this lambda A Boolean subalgebra is in fact the full clopen algebra. And as I was saying before, PPP implies this condition. So PPP is equivalent to closure of co-zero sets are open and this local condition. So A has SMP if and only if so the theorem that we got was A has SMP if and only if this lambda A is a pi base. And the Yoshida space is pi zero dimensional if and only if the local functions in A has SMP property. So this is how things shook out with SMP. So what I'd like to finish with is an example of a counterexample to the converse of this number one here, which says if A has SMP, then its Yoshida space is pi zero dimensional. Okay, so this is our construction. So what happened basically was I came up with an example and then I showed it to Tony and he generalized it, much farther. So you start with any compact space and then script Z here is some disjoint family of non-empty, nowhere dense zero sets in that space. And then for each zero set, you choose a function in D of X that's greater than or equal to 1, and it has the points in this nowhere dense zero set. Those are exactly the points where it takes the value plus infinity. So it's real valued everywhere else except at the points in this particular zero set. So we have one function for each zero set in our script Z. Capital S here is just the linear span of those F sub Z's that we chose. And then we call A of X. So the data here is X and the zero sets, and I guess the associated functions. And the object we get is C of X plus these. So you take all the bounded functions on X and you add in just these functions from D of X that are in S. So we add on a few more functions that take the value infinity at these various points. And what we proved is that this always gives you a W object with Yoshida space, the underlying space X. Okay, so my original proof was actually in this case, was something like this case with the Cantor set. But to prove the full theorem, we needed to use a partition of unity. So we needed some technology to actually make the case go in general. All right, so here's the specific example. So you let X be the Cantor set and choose any non-empty clopen subset whose complement is also non-empty. And then call them Y and W, just for short. And then in Y, choose a countable dense subset, and in W, choose a countable dense subset. And then the nowhere dense zero sets are just going to be the corresponding pairs. So for each n, we have one of the dense a Y sub n and a W sub n, and those 2 points together, that's one of our nowhere dense zero sets. And then just pick any F sub n's that that take the value plus infinity. So f sub n should take the value plus infinity exactly at y sub n and w sub n. And you can do this however you like. Then this construction yields us a W object that has Yoshida-based, the Cantor set, which of course is zero dimensional. So therefore pi zero dimensional as well. But it doesn't have sufficiently many projections because if you look at the collection of functions that vanish on W but that are bounded on Y, then that will turn out to be a band that has no non-zero projection band contained inside it. Because if you look at a projection band would have to correspond to a clopen subset of Y, then and that clopen, non-empty clopen subset of Y if it was a non-zero projection band. And then it would have to contain some point, one of these Y sub n, so it would take the value plus infinity. And so that function, the corresponding f sub n will witness that you can't that this potential projection band is not a maybe I'll just say one last thing, which is that in Wechsler's paper, so Wechsler has an example with demonstrating the same thing. And it's only 3 or 4 paragraphs. And so I went on Google Translate and I tried my best to translate it. And I got a rough sense of what he's saying, I think. And so just quickly, I'll give you a sense of what his looked like. It was interesting because he starts off with an example that he attributes to Kaplansky. And he cites Birkhoff's book, a lattice theory book. So I went to Birkhoff's lattice theory book, I tried to find, and eventually I found Birkhoff mentions this example, a certain example due to Kaplansky, but he says very little about it. And so then I tried to find this example in Kaplansky's papers and I couldn't find it. So I don't know if it was just private communication or, but anyway, so this is sort of more elaborate version. You start with our construction and you start up with an X collection of zero sets and an S as in the previous slide. And now you choose a zero dimensional cover, any zero dimensional cover of X with covering map tau. And then you look at the pre-images of the zero sets and these functions that take infinite values. And then on Y, on the bigger space, you can run our construction then, and you get this example with Yoshida space Y. And if you do this, say, for example, with X being the unit interval and Y being the Gleason cover or the absolute or whatever you want to call it, then it has all these properties. So it's connected. It has more than one element. Every point in the original space is a G delta. The covering space is zero dimensional. Not extremely disconnected. The zero sets you start with are just the individual points themselves of the space. Then our construction gives you a W object that has a zero dimensional Yoshida space, and this lambda A is as small as it possibly could be. So in some sense, it's as far from having SMP as it could possibly be. We think this is roughly what Wechsler was doing. But this is a more general version of what he was doing. And in fact, I think our previous example can be made to have the same conclusion. So as long as you pick your dense subsets carefully, I think you can also get lambda A to just be the empty set and the whole space. Okay, so that's
Questions?
Yeah.
So sufficiently many projections, that says every non-zero band contains a non-zero projection. So in terms of like turning that into rings, I'm saying any annihilator ideal would contain the annihilator of an item or a sum. So there's something called almost PP ring. PP ring is the basic idea of a projectile. There they want every, have you looked into, I'm trying to phrase it in terms of the these spaces. Every band is the joint of projection bands beneath it. That would be stronger. Because yours is just saying one. This is just saying, nah, I've got, any take it, any one in, any element in there, it's gonna live in the projection band. In there, that seems stronger. Did that come up at all in what you all are doing? This seems a little.
Yeah, I think it did in some sense. I mean, we're working on another paper now, just about sufficiently many projections. And I think as of right now, we have 1,000 ways of saying it, different ways. And some of them sound like what you're saying, or similar to what you're saying.
Okay,
But I'm not
maybe
sure.
prove that they're the same, because I'm trying to think.
They might, it sounds similar to something that is the same, but I'm not sure. I'd have to look at the paper.
So if you took a band and simply took the joint of the projection bands within it.
Yeah.
Right, what you're saying is that you should get all the way up to the band.
I'm asking, yeah, I'm not. Maybe it's denser
There's
than
another condition, right? I mean, that defines another interesting condition at the same time.
Yeah, there's some, I think, I don't remember exactly how it's phrased, but it's something like, there was an issue with cardinality too, countable, if something's a countable union of projection bands or something like that. It was different from higher cardinality or was equivalent. Oh no, wait, no, it was, anyway, I don't remember exactly, but yeah, something along these lines came up.